Alright, in this video we're going to take a look at units, standards, and the SI system. A big takeaway from this concept is that units must be specified along with the number. If I told you that I got the answer 8.2, that wouldn't tell you very much. 8.2 could be anything. 8.2 could be 8.2 meters. It could be 8.2 kilograms. It could be 8.2 boogers. It could be 8.2 strands of hair. It could be 8.2 seconds left to live. The only way to give a number a meaning is to give it a unit. Likewise, giving the number, for example 8.2, a unit also tells you what scale you're on. Right? 8.2 kilograms. That's about the mass of your backpack. Whereas 8.2 grams is about the mass of a very small handful of M&Ms. 8.2 milligrams could be about the size of 1/3 of a standard Tylenol. 8.2 micrograms could be a size that is nearly invisible to the naked eye, and 8.2 nanograms could not be seen without microscopic improvement. So the unit has to be specified along with the number, and that's going to be true throughout all of your scientific practices. Any number that's written without a unit we can consider to just be wrong, and that's going to be true in your AP test assessments as well. So let's go ahead and let's start out with the units that we use in the SI system. Some of these, or all of these, should be familiar in some capacity because you've taken science classes before this one. I want to work a little bit on the camera's ability to focus right now. It's just a little bit of a mess. So let's see if we can get it to do a little bit of a better job focusing, and I like that better already. Just don't mess up. Alright, so if we're measuring length is done in a meter, and you should notice from your text that a length was originally established to be a fraction of the distance between the equator and the pole, and 1 meter was established. It was a calibrated rod to be exactly 1 meter, and that distance between the equator and the pole on Earth, it was going to be a 1, 2, 3, let me count, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So it was this fraction, 1/10 millionth the distance between the equator and the pole was where the meter originally came from. And so all length-based units in the SI system are based off of that meter. And in our class, you're going to be using, for a meter, you're going to be using a meter stick, or you could potentially be using a smaller version of a meter stick, a fractionated meter stick, or you could use a metric tape. For time, we use seconds. All right, minutes, hours, days, weeks, those are not part of the SI system. Seconds are the only SI measure of time. You could, however, report things in kiloseconds or nanoseconds, but they must be in seconds in order to be a part of the SI system. And currently, our unit, the second, is defined based on the radiation of a cesium atom. So it's become incredibly precise. For mass, we use the kilogram. The kilogram is the base SI unit for mass. A kilogram is approximately, on the surface of the Earth, about 2.2 pounds in equivalency. So if you ever need to do an on the surface of the Earth conversion between the English system and the SI system, you can use that 2.2 pounds equals 1 kilogram conversion, but be very careful because pounds is a unit of force, right? It's a weight, whereas mass is done in kilograms. So that conversion only works if we're talking about things on the surface of the Earth, and we're going to discuss that in this class. Now that we've established our basic SI system measurements, you can take a look at some of the prefixes. All right, the prefixes that we're going to be using in this class is kilo equals 1,000 of a base. Centi equals 1/100th of a base. So for example, if we had 1 meter, right? 1 meter could be represented in kilometers or centimeters. And we're going to get that focus back. Left-handed people problems. All right, so it takes 1,000 base, so it takes 1,000 meters to equal 1 kilometer. Therefore, 1 meter is going to be equal to 1,000th of a kilometer. All right, and likewise, 1 centimeter is 1/100th of a base. Therefore, 1 meter is equal to 100 centimeters. And in your text, you're going to notice that you have a table that tells you all of the prefixes that you could potentially use in the class. And I'm going to show that to you because you might have made a note of it, but I'm going to show you which of these you probably want to go ahead and put on a note card. Because if you have them on a note card, then you're going to be able to use a quick reference. Here's their abbreviation, and here's their value by powers of 10. So if you have any questions about those powers of 10, you might want to go back and watch that scientific notation video if you haven't already, or watch it again. So the most important ones that we're going to take a look at in this class, you want to make sure that you are familiar with a giga, mega, kilo, centi, milli, micro, and nano. Those are going to be the ones that we use most frequently as prefixes for any of our SI units. So very quickly you can convert back and forth between them if you know what their value is. And let's take a look at that example. Alright, so I showed you the important ones. Just to go over them again, the important ones are going to be giga, mega, kilo, centi, milli, micro, and nano. Be prepared to use those on your next assessment. So giga, G, mega, M, K, C, little m, mu, and n. Giga is 10 to the 9th, mega 10 to the 6th, kilo 10 to the 3rd, centi 10 to the negative 2nd, milli 10 to the negative 3rd, micro 10 to the negative 6th, and nano is 10 to the negative 9th. Let's take a look at using these as conversion factors. Alright, so let's say I have a value 3.4 times 10 to the negative 4th meters. And I want to display that in terms of millimeters. Alright, so what I'm going to do is I'm going to convert it based off of the value given in this column. Right? So in this column, I know that 1 meter is in comparison, the micro is going to be, so 1 meter in comparison, the millimeter is going to be a 10 to the negative 3rd millimeter. So that means that I'm going to be converting or changing 10 to the negative 3rd meter is 1 millimeter. Sorry, I'm going to rewrite this for you just because when I get a little messy upside down in my writing, I don't want to confuse you guys. So again, we're going to be changing 3.4 times 10 to the negative 4th meter. Right? So in order for us to convert, we have to have a meter on the bottom, and 1 meter in the equivalency to 1 millimeter. Right? a meter is actually a 10 to the negative third of 1 millimeter. So that means that the meters are going to cancel out, and our overall value of 3.4 times 10 to the 1st. Because if you subtract a negative, it becomes a positive. So that means that because a millimeter is so much smaller than a meter, it actually makes this number larger by a magnitude. All right, and that's going to be how you're going to use your prefixes to do conversions. And again, that's table 1.4 on page 9 that you're going to take a look at. So the values that I've given you come from the SI system. The SI system is sometimes also called the MKS system, where the M stands for meters, the K stands for kilograms, and the S stands for seconds. So that's the meter kilogram second scale or system. All right, and in the SI system, there are base quantities and there are derived quantities, and we're going to take a look at what they are, because everything in the SI system comes from the MKS. A base quantity is defined in terms of a standard. So like I said, a second is defined in terms of the decay on a cesium atom. Meters now are no longer defined by the distance between the equator and the pole. They're actually defined based on the time that it takes light to travel between different distances, because it's much more efficient and much more exact to measure a meter that way. So originally we used length to establish the speed of light, but now that the speed of light is so well established, we use it to confirm and calibrate and standardize our length. All right. A derived quantity is derived from the base, and I'm going to give you some examples of derived quantities that should help simplify that perspective. For example, all right, velocity is given in meters per second. Velocity units are entitled, they're a rate, they're meters per second. But if you look, that velocity came from a base unit, meter and the second. Both the meter and the second are dependent on a standard. So that makes velocity a derived quantity. A kilogram meter per second squared is a newton, and that's used for force. The SI system unit for force is a newton, which is the same thing as kilogram meter per second squared. If you look, the kilogram, the meter, and the second squared are all base quantities that give you a newton. So that's a derived quantity. And then you have kilogram meter squared per second squared, which is a joule, which is the energy unit. That is, again, based on these base units. And so the SI system gives you all of the units that we're going to need. And we took a quick look earlier at how to do unit conversion. I'm gonna be honest. I started writing these notes for this video last night. I was a little bit tired, and I was having a conversation before bed. The TV was on, and I was getting ready to explain how you convert units. And I wrote the words "the units," and then I was going to explain what they're used for and how you convert them. And then I started writing the units were all hanging out, finding their similarities. I didn't really know where I was going with that. It was just I was having a moment, so sorry about that. What I really want you to take a look at is we can convert one unit to another if we know their relationship. Converting units based on their relationship is called dimensional analysis. And you use equivalencies in dimensional analysis. And I'm going to use a really straightforward equivalency. 1 inch equals 2.54 centimeters. This is an equivalency. These two are equal to each other. If I rewrite this equivalency into a fraction, right? I divide both sides of this equation by 2.54, and I get 1 inch divided by 2.54 equals 1. Alright, so if I turn this into a fraction, no matter which way I go, if I put the 2.54 centimeters as a numerator or a denominator, it equals 1. If you divide a number by a number, it equals 1. If you multiply a number by a number, it equals 1. I can put 1 in an equation and not change the value. So take a look at some of these, what we're going to call conversion factors. Right? These conversion factors are derived from equivalencies, two numbers that equal the same thing. Right? 5 meters divided by 5 meters equals 1. 100 centimeters divided by 1 meter equals 1 because there's 100 centimeters in a meter. 60 seconds divided by 1 minute equals 1 because there's 60 seconds in 1 meter. So these are conversion factors. And I'm going to tell you a little bit about the identity property. Alright. The identity property says that any number multiplied by 1 is equal to the original number. Alright, so think about this. 21 times 1 equals 1. 5.8 times 10 to the 0. 10 to the 0 equals 1, so that's going to equal 5.8. I did a little typo over there, but 21 times 1 equals 21. 5.8 times 10 to the 0, which is 1, equals 5.8. So that means that we could use a conversion factor, an equivalency. I could say 2.4 times, and we'll call that an inch, and we'll say 2.54 centimeters divided by 1 inch. Alright, this 2.54 centimeters equals 1 inch. This is an equivalency. It's a conversion factor. The inches cancel out. 2.4 times 2.54 gives you the number 6.096 centimeters. That's the same value as 2.4 inches. It's just written in terms of centimeters. This is dimensional analysis. The identity property says that 6.096 centimeters is equal to 2.4 inches. And that's what we're doing anytime we do dimensional analysis. So I'm going to do one more example here, 36 weeks. And I want to know what that value is in days. So I'm going to use equivalency. Well, I know that in 1 week we have 7 days. Alright, that's an equivalency, so I can multiply that number together. I also know that in 1 day there's 24 hours. And I also know that in 1 hour there's 3,600 seconds. If you don't know that one, you're going to learn it in physics, but you could also just do minutes to hours, seconds to minutes. But now I can get rid of weeks, cancel with weeks, days cancel with days, hours cancel with hours, and my equation is going to be 36 weeks times 7 days times 24 hours times 3,600 seconds, all over 1. So that means that there are 21772,800 seconds in 1 week. This number, 36 weeks, is equal to this number in seconds. So that gives you an idea of how to do dimensional analysis with the units. We can likewise cancel units when we're converting with prefixes. If I have 10 to the negative 9th megabytes, all right, I can turn that into regular old bytes. All right, regular old bytes, let's come up with the relationship. All right, in 1 megabyte, we refer back to table 1.4, and a mega is 10 to the 6th, so that means that it's 10 to the 6th bytes in 1 megabyte. So that means that in the end, 10 to the negative 9th megabytes is actually just 10 to the negative 3rd bytes. So that's using dimensional analysis, the identity property, to do a unit conversion. So that's going to conclude measurement, and more or less that's taken us through almost all of the examples. I'm going to create a second video to do example 1.3, example 1.4, and example 1.5, and that ought to wrap us up.